next on is
Shall I, Chester? There are amplitudes in ADS.
Right, thank you for the invitation. We started working on instability this past year, so I'm happy to get started with you. This is based on two papers from last year with my postdoc, Elion Zhang, who's now becoming a professor in China for a couple months, as well as Tobias Hansen, who's an excellent postdoc here. Okay, so let's begin by discussing the Virasor sparing amplitude. This is possibly the most basic quantity in string theory. In some sense, this amplitude came before string theory, kind of inspired string. So it has a very simple form. It's just this ratio of gamma functions that you see here. Where the STU, these are Mandelstam variables, which are defined in terms of the n-dimensional momentum in the usual way. So we put in this string length here, so dimension. So this describes the scattering of closed strings at tree level, i.e. leading order in string coupling. But what's nice about it is that it's for finite n, so for any value of the string length. Where does this quantity come from once you know string theory? Well, the whole point is that you can compute it using the world sheet, which means that it can be expressed as a two-dimensional world sheet integral, where z and d bar are the usual world sheet variables, as shown right here. So what are some of the defining properties of this Virasor spare amp? First of all, the poles in terms of the Mandelstam variables correspond to all the particles that are being exchanged. So you have one massless graviton multiplet, and then there's an infinite tower of massive multiplets whose mass goes like inverse string length squared. That's why we don't observe them in data. Another property is that because you have this amplitude for any energy, particularly you could take the high energy limit, where S and T are big and the ratio is fixed, it's called the Gross-Mendel limit, in which case the amplitude decays exponentially, in contrast to a corresponding amplitude in field theory, in which case it would decay polynomial. For instance, like 1 over S plus an L. That's one of the defining properties of string. You can also look at the low energy expansion when the Mandelstam variables are small, in which case you get the following expression, where the leading term is the graviton exchange you would have had in some field theory of gravity. But then all these corrections are due to the higher derivative corrections to the field theory of gravity, Einstein, i.e. high derivative corrections to Einstein. So this is the R to the 4 correction, this is the D to the 4 to the 4 correction, etc. Notice they all come multiplied by zetas of odd. So that's what we know about the flat space Virasor sphere. So this talk is going to be about string theory in ADS. And the reason why we're talking about that is that our only non-perturbative definition of quantum gravity is string theory in ADS. And so the defining examples are type 2B string theory in ADS 5 cross 5, dual things for string Mills, or type 2A and ADS 4 cross CP3, dual ABGM, or something which is important for this conference is 2B on ADS 3 crosses 3 cross M4, dual to some kind of two-dimensional CFT, which in some limit is this symmetrical. So in this ADS CFT duality, the most basic entry to the duality is that scattering of closed strings is related in the CFT to a correlator of the stress tensor multiplet, such that this tree-level quantity in string theory is the leading large N term in the CFT. Which for instability people, that's what you care about because you care about the planar. So ADS CFT doesn't really solve quantum gravity at ADS because the CFT is strongly coupled and hard to study. And it's in particular, even on the ADS side, we don't know how to study it using the world sheet because we're talking about a background that involves remote flux. And the world sheet theory is just not very well developed in that case. Although there's the possibility of progress from pure spinor formalism or maybe from string field theory, but as yet there's very limited results coming to the bulk for remote flux. Whereas on the CFT side, it's very strongly coupled. So it seems like from both sides, it's very hard to actually compute anything. So this talk is going to talk about progress on actually computing things in the presence of remote flux in string. So in particular, we're going to bootstrap the ADS Virasor sphere amplitude in an expansion around flat space for all three of the ADS CFT pairs discussed in the previous slide, which are all the classic pairs. And we're going to do this just using two assumptions. The first assumption is that the amplitude expanded in ADS around flat space is given by this flat space limit formula, which is basically a Borel transform of the CFT correlator, which I'll discuss obviously in more detail later. The second assumption is that the amplitude is given by a world sheet integral, very similar to the one we saw a few slides ago. So some two-dimensional integral where we have a certain ansatz what the integrand is, will be written in terms of things called single-valued multipolynomial. And so starting just with these two assumptions and nothing else, you can completely derive the tree-level ADS scattering, at least for the first correction into ADS. So this program was started by Fernando Alday in his postdocs a couple of years ago, first an example of ADS 5. And then in our recent work, we generalized this to ADS 4 and ADS. And so we're going to start just by reviewing the ADS 5 case and then move on to the other. Okay, so let's start with ADS5. So the dual theory is n equals 4 superarea Mills. I'm sure everyone in this audience knows the properties of this theory. So that's an SU4R symmetry. It's an SU gauge theory for complexified coupling tau. The duality of type 2D string theory has the well-known dictionary where the string length is inversely proportional to n. You can define this top coupling with G and Mill squared n. And the leading 1/n squared correction, planar limit, is leading order string coupling. But you can work to all orders in 1/length, i.e. to all orders in the string. And so that's the limit we're going to consider, this planar limit. So the correlator we're going to consider is the stress tensor multiplet correlator. We're going to look at the superprimary of the stress tensor multiplet, which is the scalar dimension 2. Superconformal symmetry fixes the 4-point function to have the following form. So there's one term which is trivial, which we call the free term, because it doesn't depend on the coupling, so you can fix it with the free theory. The other term is the one we care about. This theta is some kinematic, and H is the non-trivial term that includes all the non-trivial. This is a functional conformal cross ratio. So as in any 4-point function, you can expand it in blocks by taking the OBE twice. And so because H is the only interesting part of this 4-point function, we expand H in super blocks. And in the context of this H, which is called the reduced correlator, the block expansion is very simple. And so you just have a single conformal block shifted by 4 for every even spin L, and each of these blocks corresponds to a long multiplet. Long multiplet means the scaling dimension and the OP coefficient are both unfixed. For instance, for spin 0, this would be the Conici. And then you have other long. Okay, so this is what we get just from kinematics. We find it convenient to work in Mellin space. Mellin space is basically just a Fourier transform, except instead of a Fourier transform with translational invariance, now you have a Fourier transform with conformal invariance. And so we have two variables of position space, U and V. So thus we have two variables in Mellin space, S and T. And so we take this kind of fancy Fourier transform, where the reason why we have these gamma functions is that poles in S, T, and U, they correspond to the scaling dimensions of exchanged operators in the Mellin average. And so if you're working at tree level, we know from large N counting that you should only exchange single and double trace operators. And so these gamma functions automatically take into account all the double trace operators, such that this remaining function will only have poles corresponding to single trace operators, so it just makes life simple. So that's the motivation for this factor. Other than that, this is just a Fourier transform. So what do we know about this Mellin amplitude, i.e. the 4-point function, in the planar limit? So as I discussed, it only has single trace exchanges. And so the only single trace that can appear kinematically is the stress tensor multiplet, i.e. gravity. And so they have these poles, because recall that all single trace exchanges correspond to poles. So we have these poles corresponding to gravitonic exchanges. This is the only operator we're exchanging at tree level. So every other term, these are just contact terms, which come from higher derivative correction. And so we can organize them as follows, where these alphas are unknown coefficients. These correspond to the coefficients of these higher derivative corrections, which a priori you don't know. And we just organize them as such, where sigma 2 and sigma 3 are just polynomials in S2. And so these are just infinite possible contacts. So the goal is to fix these alphas. Because if you can fix the alphas, thus you know everything about the tree level ADS. Okay, so the first assumption we use is this flat space limit. So in the strict flat space limit, this isn't an assumption. This is a derivation. Question?
Sorry, may I ask you? So these alphas, they play the same role as the zeta functions in the flat space version?
No, the zeta function is the actual one. These alphas are unknown. So the goal is
exactly, but so I mean, you have zeta 3,
indeed.
zeta 5, and so on, and you want to fix the alpha to some numerical values, which play the same role.
So alpha 0 would be those zeta 3, zeta 5, etc. Alpha 1 is the unknown. Because alpha 0 is the flat space limit, which we know. Alpha 1 is the first ADS correction, we don't know. Okay. Yeah, good question. Yeah.
What are the double traces?
The double traces are in these gammas. Because I mean, the double traces in the planar limit are pretty trivial. I mean,
You don't have poles corresponding to double traces.
we do. These gammas are poles.
Sorry.
That's where we put those gammas.
I see.
Okay, so there's something called the flat space limit. This is rigorously derived by Panadonis, 10 years ago, and it says given a CFT correlator within a Mellin space, this is how you get the corresponding flat space amplitude. By basically taking a Borel transform, which is what this integral over alpha is, and taking the top coupling lambda to be very big. So basically, you're rescaling S and T by this squared lambda, and then taking lambda goes. So this is rigorously derived. The non-rigorous assumption we make is that this flat space limit formula should define the ADS amplitude away from the flat space. So the flat space limit, this is rigorous derivation. A0 is the flat space limit. The fact that we could use the same Borel transform to define A1 or A2, which are these ADS corrections, that is an assumption. But we'll see much evidence for this assumption in the following slide. So if we want to take this expansion around flat space, and if flat space comes from basically taking lambda goes to infinity, then clearly we want to look at very heavy operators. That's what we're sensitive to in flat space. We don't see light operators near flat space. So if we want to expand the CFT data around flat space, well, first of all, every integrability person should know that the single trace operators are lambda to the border in flat space, for instance, like the Konishi. And then we have various wonderful lambda corrections, corresponding to ADS corrections. The OP coefficient, maybe this isn't as obvious, but this basically follows from taking conformal blocks and then applying this Mellon transform and then applying this flat space transform. And so when you do that, you kind of naturally see that this coefficient pops out. The intuition behind this sign squared is that this is due to mixing between double trace operators of really big dimension and single trace operators. Because in principle, they could have the same dimension. And so that's what this, and that's why you have these like zeros corresponding to this sign squared. Anyway, so after stripping off this factor, you then also expand the OP coefficient squared in 1 over lambda, as you see here. And so this is the expansion around flat space. F0 and tau 0 are the flat space answers. The goal is to get this tau 1, tau 2, F1. Okay, so we now apply this flat space limit formula to the block expansion. So we do two transforms. We go to Mellon space, and then we go to like around flat space, this Borel transform. And after you do that to the conformal blocks, it's just some group theory calculation. You get the following form for the blocks as an expansion around flat space. So indeed, you see the sine square factor kind of pops out. You have this 1 over lambda expansion, which is around flat space, and then these R's are basically functions of Chebyshev U polynomials. These functions are expected because in the strict flat space limit, these are just 5-dimensional partial waves. And we expect that conformal blocks become partial waves when you take the flat space. The fact that you get this away from the flat space limit is perhaps not so surprising because some kind of perturbation away from so the first check we can do is that we can see in the flat space limit, if we compare this to the known flat space Virasoro-Shapiro, are they consistent? Of course they are. And they are consistent as long as this flat space limit value of the scaling dimension, or actually the twist, tau 0 is 2 square root of delta, where delta can be any integer. So delta is basically the mass load, in the integrability level. So for instance, the leading Reggery trajectory is when the spin is related to delta as 2 times delta minus 1. And so the Konishi operator would be spin 0 if delta equals 1. And then you have kind of like infinite spin generalizations of the Konishi operator. You also have higher Reggery trajectory. You can similarly fix the OP coefficient in the flat space limit. You get some more complicated formula. I should note that the only operators that we can really read off uniquely are the leading Reggery trajectory, because all higher Reggery trajectories are rejected. And so that's why we're only going to focus on the leading Reggery trajectory in the stock. If you want to get the other Reggery trajectories, we'd have to input data from integrability, or you would have to look at other reports. Okay, so this is just the flat space limit. This is a big trick. Question?
Yes, sorry, can I just check? So you've got an ansatz for the flat space limit. You have an ansatz.
No, we haven't used the flat space limit we know. It's the Virasoro-Shapiro.
Okay.
Yeah, so that's not enough. So we know the flat space limit, Virasoro-Shapiro. So far we're in the flat space limit.
You have an ansatz for
the correction. Yeah, but we haven't yet discussed.
Okay.
Yeah. So far there's no assumption. So far we're just taking the strict flat space limit. There, everything is perfectly just. The assumption is going to be that you can define the ADS correction using this flat space limit Borel transform.
And then it's matched.
Yeah. So that'll be the assumption. But so far we haven't used it. Okay. So now we look at the first correction away from flat space, which is 1 over lambda quarter. Now we expect that the amplitude shouldn't have such a correction, basically based on dimensional analysis. But the CFT data can have such a correction, and indeed it does. The correction has to be a bit trivial. So basically, if we assume that the answer for the amplitude should be 0, and then if we expand the blocks to this order and demand that equals 0, it fixes tau 1 and F1 to take the following very simple values. And indeed, this matches with integrability. And so if you look at the answer, say for the Konishi at large lambda, you will find that its first correction, indeed, this is the twist, so just get rid of the spin, you'll find that the first correction is -2, which is kind of the classic result in integrability. Because the answer is basically like 2, squared spin -2. As shown in this paper by Grobo Capiera back in 2020. Okay, so this is like a nice result, but we can do better. So now let's look at the first 1 over square root of lambda correction. That's much more interesting because this is the first correction where we expect the amplitude is actually non-zero. And so this is where we're going to put in our second assumption. Our second assumption is that the answer in ADS is given by a worldsheet integral, similar to flat space, where we assume that the integrand takes the following form. So it's going to be a sum of these L of z, these are functions of z, where that's like the worldsheet variable, and we assume they are weight-free single-valued multi-polynomials. Now, I won't go into detail of how you define these things. I mean, these kind of show up naturally when people are computing on amplitudes in general, which is, I guess, was kind of motivation for them. But more specifically, the reason why you want them in this context is that if you take the low energy expansion of this expression, i.e. small s and t, you will find that these single-valued multi-poly logarithms naturally give you zeta 3, zeta 5, etc. And so those are kind of the ingredients you expected in flat space. The fact that you should get the same zetas around flat space, of course, it's an assumption, but it's an assumption which will end up, giving the right answer. So it was a very smart assumption back there. So that's kind of the motivation for having single-valued multi-poly logarithms. The reason why you want specifically weight 3 as opposed to weight 4 or weight 2 is that when doing the low energy expansion, you want to make sure you have the zeta of like the right integer multiplying the right power of ST. So for instance, r to the 4 should multiply 1. It shouldn't multiply s squared plus c squared plus q squared. And you only get that right matchup if you have the right weight of the single-valued multi-poly logarithms. There's basically a similar justification for why you want to have the right polynomials here. Another related justification is that when you take the block expansion and do the Borel transform, this has poles in ST. And for this first one over lambda correction, the poles are degree 4. And so if you only want to get degree 4 poles and lower, you need to have only weight 3 single-valued multi-poly logarithms and not higher weights, because otherwise you'd have poles that are too high. So that's the other motivation for this. So basically, demanding the right pole structure and the right zeta 3s and zeta 5s, etc., that basically fixes you to weight 3 and polynomials of a certain name. Now, of course, there's still an assumption that we're even looking at the space of single-valued multi-poly logarithms. We could have looked at other single-valued, functions in principle, but that's an assumption. And so with this assumption and comparing against the block expansion, it turns out this uniquely fixes the first ADS correction to the amplitude, which is very surprising. Because first of all, these assumptions could have just been wrong and you wouldn't have found any solution, or they could have been insufficient and you could have found many solutions. But it turns out you find one solution. Okay, so now that we have our solution, we can read off all data, at least for the first ADS correction. So in particular, going back to this way of writing the Mellon amplitude, we can read off these alpha 1s, which is the first ADS correction to flat space, which is alpha. And so, for instance, this allows us to completely fix the d to the 4 r to the 4 correction, because d to the 4 r to the 4 is just written in terms of flat space plus the first ADS correction. It doesn't have any more ADS correction. So we know d to the 4 r to the 4 completely is proportional to zeta 5. And the first consistency check is that this d to the 4 r to the 4 correction in ADS was fixed several years ago by me and Silvio by imposing 2 constraints from localization. So this was a totally independent method. We use that to fix d to the 4 r to the 4, and lo and behold, it matches Fernando's. And so that's like one check on his approach. Furthermore, if you take our 2 localization constraints and combine them with these new constraints from Fernando, you can actually fix all the way up to d to 8 r to the 4, which is the first unprotected correction. And so this is very interesting, because in the past, people thought that analytically you might only be able to ever fix, protected correction. And here we've got an unprotected correction, which shows that the assumptions Fernando put into his program are really going beyond, stuff like localization, which is pretty. So that's very surprising. The answer is proportional to zeta 7, which is, I guess, what we would have expected. But there's more checks on this answer. So we can now we can take the high energy limit, which again is S and T large with the ratio fixed. Recall that in the flat space limit, this had the Gross-Mendes form of this exponentially decaying function. So for the first correction, you get this function times something called W3, which is some combination of weight 3 single-valued multi-poly logarithms. So this might seem like a very random combination, but you'll see in a moment this actually shows up in other contexts. But so far, this is just the result. Perhaps it doesn't seem so much. Finally, the most interesting check that this conjecture is correct is that we could read off the CFD data of the lowest Reggie trajectory. So in particular, we can read off the twist, which is scaling dimension minus spin of this lowest Reggie trajectory. It takes the following form. So this is the flat space answer. This is the first correction. These are the 2 ones I discussed before. And now this is the first ADS correction, which is basically the first one over lambda correction. And so these were computed independently from the quantum expectral curve by your community back in 2012. And lo and behold, it matches on the nose. And so in my opinion, I think this is the strongest check of Fernando's program, because it's an extremely non-trivial function and you exactly match it analytically. from the integrability perspective, they had computed this thing numerically just by doing fits. Whereas in Fernando's approach, you actually get these analytic methods. Furthermore, you can go beyond scaling. You can also compute OP coefficients because you can compute all CFT data at this order. I won't show the formulas because they're a bit uglier, but you can also get them to the same order. And recently, these OP coefficients were also checked. There was this beautiful paper by Simo Karen Huo, Frank Coronado, and Zarazare, where in the planar limit, they combine numerical bootstrap with integrability with supersymmetric localization, basically combining everything we know, and they use that to fix the basically the OP coefficient of the Konishi in the strong coupling regime. And lo and behold, numerically, it precisely matches Fernando's prediction. So basically, everything Fernando predicted has been checked, which is a very strong evidence that his assumptions are probably correct, even though we don't understand why. At least in the context of ADS. Okay, so now we could talk about the next ADS correction. And so to go to the next order in 1 over lambda, now you assume that the worldsheet ansatz, instead of being weight 3, you assume weight 6. This is kind of a natural assumption because when you do the block expansion and expand to this next order, you start getting poles of weight 7, and like weight 6 naturally leads to poles of degree 7, and so that's kind of the motivation. And so when you combine the assumption of the block expansion with this worldsheet ansatz, now you don't completely fix the answer, unfortunately. You have to put in some data known from integrability. So in particular, if you put in the known answer for the Konishi, which in my language I call tau 10, then you can completely fix the answer. And so in particular, you can then make a prediction for the rest of the longest gradient trajectory, which takes this fairly complicated form. And again, this beautifully matches the numerical prediction from integrability just from 2 years ago. So this is even more non-trivial evidence that these assumptions are giving the right answer. It's not just the first ADS correction, it's also for the next ADS correction. And then again, you can combine with localization to get this very unprotected correction you didn't send out before. You can also take the high energy limit. You find that it's kind of the square of the first ADS correction high energy limit, which is kind of interesting. I should also note that people also generalize this result. So this was for like the 4-point function of gravitons. People also generalize it to the 4-point function of other KK. And so now for 4-point functions of any KK modes, we have the first ADS code. Okay, so that's the story for ADS5. That was the review. Now moving on to the new results from the last year and a half. First for ABGM. So ABGM, hopefully some people are familiar with it. It's a 3D gauge theory with 2 gauge groups with opposite Chern-Simons coupling, which has n equals 6 supersymmetry when k is bigger than 2, which is what we're going to talk about, and SO6 R6. It has 2 discrete symmetries. One of them is space-time parity. Another one might be less familiar. It's a certain Z2 symmetry that extends the R symmetry from SO6 to O6. The ADS-CFT dictionary is similar to ADS5 process 5. So you have string length inversely proportional to n. Now you define the top coupling as basically n over k with some correction, instead of ADS5 where it was Gn squared. So k is kind of like the inverse of the coupling. You can also relate the string coupling to n and k as follows. This CT is some function of n and k, as shown here. It's a convenient way of packaging things because it's related to the coefficient of the stress. So we're going to work. Question?
What is the another A2 symmetry?
Well, I just defined it. It extends SO6 to O6. Yes. So we're going to work in the planar limit, i.e. leading order large n. And so in the planar limit, we are blind to parity. One way of seeing you're blind to parity is that, like, when you're in planar limit of large n, you don't really know if this is u of n or u of n plus 1. And that would break parity if it was u of n plus 1 instead of u of n. But we just don't see that in leading order. So you don't see parity. But you do see this other Z2 symmetry, which extended SO6 to O6. So we're going to call this Z, and this is going to be very important in one ball. Okay, so the rest of the algorithm is extremely similar to what we already saw in ADS. So in particular, we look at the 4-point function of the stress tensor multiplet. We expand it in super blocks. The super blocks are worked out by me and my collaborators back in 2020. So you have a different super block for every single super multiplet. It's a bit more complicated than ADS5. Because for ADS5, we have like a reduced correlator, and so you could write everything just as a sum of just a single block for every long multiplet. We don't have a reduced correlator here, so things are much uglier. So these super blocks are complicated linear combinations of blocks, but we know what they are. There's also protected multiplets, whose scaling dimension is fixed, but they won't be relevant for us because we want to work in this expansion around flat space, so we're going to look at very heavy operators. And so the protected multiplets we can basically ignore. So we only care for the long multiplets, but unlike ADS5, there are now multiple long multiplets that appear in this format. So first, and we can characterize them by how they transform into the 2 Z2 symmetries, parity as well as the Z symmetry. So when the spin is 0, it turns out you have 3 possible long multiplets, basically you can define one that's parity even and Z even, and one that's parity odd and Z odd, and then there's like one more combination. Sorry, there's only 2 combinations. They're both Z even, one's parity even, one's parity odd. You also have blocks where the superprimary is odd. In that case, it's both Z and parity even. And when the spin is even and bigger than 0, then you have 3 combinations, which is parity and Z even, parity and Z odd, and parity odd. So you basically have a much richer spectrum in this 4-point function than you had in ADS5. In ADS5, you basically just only had even long multiples. Here you have a whole variety of them. Okay, so just as in ADS5, you take the Mellon transform and just define it a little bit differently. And again, the tree level answer is written as some meromorphic term, which is just M supergravity, plus a bunch of polynomial terms, whose coefficients are zetas. So it's very similar to ADS5, just the expressions are a little bit uglier because you have less supersymmetry. And again, the goal is fixing the coefficients of these polynomial corrections, which correspond to the higher derivative corrections to supergravity. So again, just as in ADS5, we have a flat space limit, which is given by this Borel transform, which is just slightly different than ADS5. It's just given in Pennadonis paper. And so again, in the strict flat space limit, this is rigorous, that this gives the flat space limit of the ADS amplitude. But we will assume that this Borel transform also defines the ADS amplitude beyond the flat space. And so we can just take the blocks, do a Mellon transform, and then do this Borel transform and expand them in lambda, just as we did in ADS5. And then demand that equals in the strict flat space limit the very source 0. And just as in ADS5, we get the expected answer that the flat space value of these cows is 2 squared of delta, which remember delta is any integer. And this is the same for all spins and for any Z. It's just a universal answer. If we now go to the next order, 1 over lambda is the quarter, we know the amplitude vanishes there, and so demanding that the block expansion vanish, that fixes the first correction to tau 1 just to be minus spin minus 3/2. It also gives some constraint on the OP coefficient. If we go to the first non-trivial order, which is 1 over square root of lambda, we again write a worldsheet on top to weight 3 single-bed multiple logarithms, just as we did in ADS5. And again, we find a unique solution. And so this was very surprising when we saw this. Because the way I'm trying to present it, I'm trying to say, like, look, it works exactly the same as ADS5. But when they did it in ADS5, I mean, Fernando himself told me he didn't expect this would work in any other dimension. Because it's kind of like a wild assumption that this flat space limit formula should give you anything reasonable beyond the flat space limit. I mean, you might even ask the question if you're even preserving supersymmetry in some sense. Because in ADS5, you have this reduced correlator, which like automatically preserves supersymmetry. Here, you don't have a reduced correlator. Maybe you would have thought supersymmetry was screwed up. And yet, lo and behold, again, it works in that you find a solution and you find a unique solution, which is particularly interesting. Okay, so once you have the solution, you can learn about all this information, very similar to what we learned in ADS5. So first of all, by taking the Leonard expansion, you can fix the R to the 4 correction. You actually can't fix the R to the 4 correction. Because to fix R to the 4, you would need the flat space answer as well as the second ADS correction. And so with the first ADS correction, it's actually not sufficient to fix it. You can take the high energy limit, and this is where we get our first very surprising result, which is that when we took the high energy limit of ADS5, I told you the answer was the flat space limit times the W3. When we take the high energy limit of ADS4, we get the exact same answer, completely identical. And we have no reason why these should be identical. So this is a mystery which is looking for an explanation. So somehow the high energy limit in ADS, there should be some kind of universality, which we don't yet understand. And so that's why when I showed you this W3 a few slides ago, I said it looked a little bit ugly, but it's actually very interesting because it's showing up in 2 very different contexts. And before we took the high energy limit, the answer looked completely different. Like it's only a high energy limit that it's in. So this is kind of a question we would like. So now we can compare to integrability by reading off the CFD data. So remember that we have different long multiplets that are organized by their Z symmetry. So when the spin is odd, there's just one family of operators. When the spin is even, though, we either have Z even or Z odd, which we put tau plus or tau minus. And so this is what the answer looks like. So you have the leading order correction, which is what this 1 is. And that's very similar to 4D. Then you have the first 1 over lambda to the quarter correction, which is just some kind of shift. Curiously, the shift is a fraction instead of 2. And then most non-trivially, you have the first 1 over square root of lambda correction, which is these very trivial functions of the spin L. So now we can compare this to integrability. So some of these results were computed using integrability. So just a few years ago in 2018, these authors computed the spin 0 Z even guy as well as all the spin odd guys. And that precisely matches our prediction. So that's again another very non-trivial check that our assumptions are correct. But they did not compute the Z odd guys for even spin, because I think people just weren't aware of the Z symmetry. I suspect this is why they didn't compute these operators. So I'm told that some of these authors are working with Tobias now to try to compute this using the quantum spectral curve and further match our corrections. But I mean, it's still work in progress. But this is an example of a prediction coming from this method, which intricability might match. Furthermore, we can also read off the corresponding OP coefficients at this order for all three families of authors. Hopefully in the future, this could also be compared against some kind of numerical bootstrap calculation, something I'd like to do, but this hasn't been done yet. So there's a lot of very new predictions in both scaling dimensions and OP coefficients coming from this. So that was the first ADS correction. So just like in ADS5, we can actually go to the next ADS correction. And so again, we assume now a weight 6 ansatz instead of weight 3 as before. We can again compare this ansatz to the superblock expansion. Again, this doesn't totally fix the answer. We need a bit more data. And so to fix the answer, we can put in a certain CP data that was known from integrability, which was like the spin 1 scaling dimension, Z even, which was known. We can also put in the value of the R to the 4 correction and the low energy expansion was known from localization. And by putting in all this known data, we're able to completely fix the second ADS correction and then read off CFT data. So now this is the next one of the Landry correction. So it's an even more complicated expression. And we can compare some of these predictions to integrability. So we can compare, as usual, the Z even ones to integrability, and those indeed match. And the Z odd ones are new predictions, which again, hopefully will match in the future. We can furthermore use our results to combine with localization to fix D to the 4 to the 4, which supports theta 5. And then we can again check the high energy limit, which again is the same as ADS5, also at this order. So it also kind of squares to be, it's like the square of the first ADS correction and the second ADS correction. So basically, at the end of the day, everything that was computed in ADS5, we've computed to the same order in ADS4, even though ADS4 is much more complicated. I will say, though, that in ADS5, people did a similar calculation for four-point functions of other KK modes, whereas in ADS4, we've only done the lowest KK mode because it's much, much more complicated. You know, people don't even know the word identities for other KK. Okay, so that concludes ABGM. Now we can move on to the last example, which hopefully should be of the most interest to this community, because apparently you guys are ADS3 people. So now let's talk about ADS3. So Swadrini reviewed before, these theories all have small n equals 4 supersymmetry, half maximal supersymmetry with an S2 cross SU2R symmetry. So we're going to talk about the two cases with the small n equals 4, which is where this four-dimensional compact manifold is either K3 or T4, which is dual to some kind of 2D CFT, of which is not that much to come up. So the basic ADS-CFT dictionary, as reviewed before, is that the string length is inversely proportional to the square of the sum of two different contributions. So unlike in ADS4 and ADS5, where you only have Ramon-Ramon flux, now you have either Ramon-Ramon flux or an SNS flux or both. So K corresponds to SNS flux and it's an integer, and GSN is the Ramon-Ramon flux, and this is pretty much any real number, because GS can be anything you want. So there's two theories one can look at, the T4 theory or the K3. T4 has 20 moduli, K3 has 84 moduli. And we are going to consider, of these many moduli, in each theory, we're going to consider the 4 moduli that do not depend on the compact spacetime and 4 in the planar limit. So these moduli in the CFD, these are dual to the dilaton multiplet in the ball. And so it's because it's the dilaton, that's why it doesn't care about this compact spacetime. So that's why in the planar limit, we actually get the exact same answer for K3 and T4. This is some kind of like universal stuff. So in more detail, we are looking at the multiplet in the CFT, whose superprimary is dimension 1, it's half BPS, and it has 4 top components which are marginal, and they correspond to these 4 marginal. And so the 4-point function of these CFT operators is dual in the bulk to scattering of these dilitons, which basically is closed string scattering. So thus, in the flat space limit, it is again the Virasoro amplitude, which is why we can run this out. Okay, so everything else follows very similarly to what we just discussed in ADS5 and ADS4. So we look at the 4-point function, we fix it using supersymmetry. This is very similar to 4D. We have some trivial free term, we have a kinematic function, and then we have the non-trivial H. We expand H in blocks, very similar to 4D. The blocks take a slightly different form. They're shifted by 2 instead of 4, U inverse instead of U minus 2. We take a Mellon transform similar to higher dimensions. The Mellon amplitude, again, has poles corresponding to the exchange of dilitons. which is the graviton mode, and then polynomials corresponding to higher derivative fractions, very similar to higher dimensions. Again, we take this flat space limit, which is some kind of Borel transform, which is a slight variation of higher dimensions. We apply this to the block expansion. In the flat space limit, we demand it equals to the flat space 0, that fixes tau 0, just as in higher dimensions. One difference between higher dimensions is that it turns out that the leading Reggie trajectory starts at spin 2, unlike n equals first Greg Mills, where it started at spin 0. So this is some kind of curious fact. For the first one over lambda to the quarter, demanding that this amplitude vanishes, fixes first correction to be minus 10 minus 1. And then for the first non-trivial order, which is 1 over square root of lambda, we again assume a worldsheet ansatz of weight for single dimensional polylogarithms. And again, we find a unique solution, which again is like a miracle. There's no reason why we have to find it. So if you are carefully following this talk and not looking at your phone, then you might ask the question of where did we so far assume that we're looking at pure Ramon flux instead of pure NS flux, or perhaps a mix of both flux? Because we haven't made that assumption anyway. All we've done so far is the usual assumptions, which is applying the flat space limit beyond the flat space limit, and assuming like weight-free single value multi-polylogarithms. And so how does that specify Ramon versus NS? And so the way we're going to check what answer we got is in a moment, basically by reading off the CFD. But before we get there, first of all, we can use our unique answer to look at the Lonergy expansion, but we can't actually fix the first hybrid correction because that would require the next order in the expansion around that. We can take the high energy expansion, and again, we find the exact same answer that we found in ADS4 and ADS5. So this is like another one of these unexplained miracles that we're getting the exact same answer. Hopefully there should be some explanation for this universality. So now we can read off the CFD data. So let's read off the CFD data of the lowest Reggie trajectory, which is when spin over 2 equals this delta. So this is the answer. So we have a leading order answer, which is, looks similar in all dimensions. We have this 1 over lambda to the quarter, and then 1 over lambda squared correction, the most interesting one here, for all the spins on this leading Reggie trajectory. Now, integrability people have not yet been able to compute CFD data at strong coupling. So of course, a lot of progress has been made, but they're not there yet. And so that's why we don't yet have a way of confirming our predictions. This is a new prediction, which hopefully will be confirmed in the near future. So I've already gotten some emails from Bogdan where he claims he's close to confirming this, but not yet. Maybe Sandrini will catch up with the TBA approach. I support both groups. And so because we don't have any integrability results yet, instead, the best we can do is we can compare it to a classical string solution. So in the early days of integrability, those who were following it, before you knew how to compute things using quantum spectral curve or TBA, instead, if you wanted to find the strong coupling expansion of, say, the Konishi, what you would do is you would write down basically a classical solution to the Green-Schwarz-Witten action. And so the way you're able to look at a classical solution is that you looked at some solution to the equation of motion where the quantum numbers are very big, such that you could do a saddle point extension. And then you would boldly extrapolate those quantum numbers to finite values in order to compare to something like the Konishi. And so people did this program in ADS5, and it worked, and it was later on justified using quantum spectral curve. They also did this program in ADS4, so it seems like a reasonable program, even though it involves this non-rigorous extrapolation. And so you could do a similar calculation in ADS3 process 3. It's very similar, actually, to ADS4 and ADS5. And so the answer you get, so J is a certain quantum number of the R symmetry, L is the spin, and so this is the answer you get. Now, you can't fix this term because this would be a one-loop correction, and that's less hard. So you can only get these first 3 terms. And so a check on our answer is that the semi-classical calculation, if you plug in J equals 1, matches our answer non-trivially if you furthermore set C to -140, which curiously is the same value of C as in ADS4 and ADS5. So this is like a semi-check on our answer from the semi-classical calculation. Also, this semi-classical calculation is sensitive to whether or not you have Ramon flux and SNS flux or some combination, because that would show up in your solution to the equation of motion. And so we are matching the answer with pure Ramon. And so this is why we think that we have kind of magically landed on the pure Ramon answer. Although why we landed on that answer is still a bit. We can similarly read off OP coefficients to the same order. They're a bit more complicated, and so this gives some other predictions. Okay, so in conclusion, we have managed to fix the first correction in ADS from flat space of this graviton scattering in all the classic examples of ADS. So ADS3, ADS4, and ADS5. In the case of ADS4 and ADS5, we've furthermore been able to fix the second ADS correction. Although in that case, we have to put in some data from localization. using this result, we were able to compute the strong coupling expansion of single trace operators, the kinds of things that integrability people care about. So we're able to compute the scaling dimensions and OP coefficients of the lowest Reggie trajectory. Radius 5, this matched the results of integrability for the scaling dimension, and for the OP coefficients to match results from the bootstrap. Radius 4, we were able to compare some of the results to integrability, other results are just new predictions. Radius 3, everything is a new prediction, although we were able to partially confirm our results by comparison to the semi-classical calculation. And radius 3 is just for the pure Ramon moments, which, as Sandrini reviewed in his talk yesterday, is the case we actually know least about. So that's kind of the irony, is that even though this is most similar to higher dimensions, you might think it's going to be easier, it's actually much harder, because for pure SNS, you have an exact solution. Whereas for pure Ramon, you have no idea what the CFT is. You basically don't know anything about it. We also could take the low energy expansion of our answer, and we could, in the ADS4 and ADS5 case, we could compare to some independent calculations from localization, which is a further check if these answers are correct. And ADS3 is just a new prediction. Okay, so there are many future directions to this program. So of course, we would want to go to more higher order corrections in this expansion around flat space into ADS. So in particular, for ADS4 and ADS5, we went to the second order. For ADS3, we only went to the first order. So it'd be nice to go to the next order. ADS3 is kind of harder though, because we don't have localization, nor do we have integrability. So we don't have as many constraints. So hopefully once integrability people catch up, we'll be able to go to the next order using it. It would also be nice if we could, okay, so far basically we've computed this ADS amplitude using assumptions. Now, in principle, we should be able to compute this somehow from string theory. You know, like string theory hopefully should be able to compute things, you know, with Ramon flux. And so the hope is that this should be possible using string field theory. So I know Sheehan is working on this with his collaborators. They've had a series of papers in ADS5 process 5, where they recently found like some kind of solution in ADS5 process 5, and I think their next step is to start computing this data. So we might actually have some kind of check from string field theory in the next couple of years. It would also be nice to make more comparisons to integrability. So for instance, the Z odd CFT data for ADS4, as well as everything for ADS3. Finally, focusing on ADS3, which is one of the themes of this conference. So ADS3 in some sense is the most interesting case, because you have two kinds of flux, NS and Ramon. And so far, it seems like the case of which we know the least about, because we don't have localization, we don't have integrability. But I actually think that in the long term, this will be the case in which we can push the furthest, for the following reason. So first of all, how do we know that we have the Ramon answer? That was from comparing to the semi-classical lines. But probably, in our assumptions, the fact that we were getting pure Ramon came from our worldsheet ansatz assumption. Because we were assuming these weight 3 single value logarithms, which was motivated by higher dimensions. So we know the answer is always pure Ramon. But for ADS3, we know that there should be the possibility of adding terms that break the worldsheet parity. Because when you turn on the NSNS flux, that breaks the worldsheet. So probably we need to expand our ansatz beyond weight 3 single value logarithms to terms that break worldsheet parity. And so I can say that we did that and it actually works and we found it. I'm just not presenting it here because we're still checking some final details. But indeed, with Fernando and Deleon and my new postdoc Yarosh Bazeri, we basically found another term which we added to our ansatz. With that term, we were able to fix an answer, and that answer matches the expected answer in the pure NSNS, which is kind of the non-trivial check. But then we can interpolate between an SNS and pure Ramon. So this will give further predictions for integrability to check from some kind of quantum spectral. Now, the reason why I think that in the long run, we can go further in ADS3 when we could go in ADS4 and ADS5 is that in ADS3, in the pure SNS limit, we know everything. So we know not just the first ADS correction, we know all ADS corrections. In fact, we know it at finite ADS3, at least in principle. So no one has actually computed this 4-point function in the pure SNS limit, just because it's a hard calculation. But the tools are all there. You just have to be very good at doing calculations in WW. And so the hope is that using this known input, once it's computed, if we could maybe impose this at every order in the expansion around flat space, and because this will give like infinite constraints, maybe this will be sufficient to actually fix the general mixed flux case, all orders in the ADS extension, which in particular would give us the pure Ramon answer, all orders in the ADS extension. Which is why I think in the long term, ADS3 might actually be better than ADS5 and ADS4. Of course, it would be nice to discuss the other ADS3 theory, which is the one with the large n equals 4 algebra, which is ADS3, process 3, process 3, process 1. For that, we basically just need the worded entity for the 4-point function we consider. This is something I'm working on with Garish at the moment. Once we have that worded entity, we should be able to do the exact same algorithm. I don't know if it will be more or less constrained. I mean, I would like to think that because it's large, it's supposed to be small, that should make it better, but I guess we'll see. But I mean, the story is very similar. I mean, like, so in this large case, you just have two moduli, and those two moduli basically just correspond to two fluxes, mono and S. So it's not like that. So another thing is that I mentioned how there's many moduli for T4 and K3, and we only focused on like those 4 moduli, which basically don't affect the compact space. So they're kind of unique in that sense, which is why we got the same answer for T4 and K3. So you might ask a question like, could you study the correlators of other operators corresponding to other moduli? So for the T4 theory, you can, because these basically correspond to other half BPS multiplets. So there's like another set of 4 half BPS multiplets, which in the planar limit transform under some approximate SO4 signature, which is basically a remnant of T duality in the planar limit. And so it should be possible to study these 4-point functions using the exact same algorithm. And in this soon to appear work, we do that, and we do find an answer for them as well. And so this will just give further predictions for integrability, because basically this means you could read off CFT data, which will be in other representations, not just the same. On the other hand, if you want to study the K3 theory now, and if you want to look at these other multiplets, this is much more challenging, because these are dual to modes in the bulk whose flat splice limit is not the Virasoro-Shapiro. And so even the flat splice limit is very hard for these other modes. And so that's why I think if we want to look at this wider class of FBS multiplets, we're kind of restricted to T4. Okay, that's it.
Thank you very much. Any questions? Yes.
So can you go beyond the planar limit here and give one-to-one corrections?
It's an excellent correction. Excellent question. It's an excellent correction and an excellent question. Okay, so basically, if you were to want to extend this algorithm, so for the block expansion is straightforward. I mean, you can go to anywhere you want. It's more what your ansatz would be. So it's like you would have to guess a natural ansatz of like one loop string scatter. And so I've spoken to some people, like Fernando's spoken to some people. There's some ideas in the literature out there because like people know a lot about what string amplitudes look like at one loop. You know, especially with this recent work of Sebastian Zera and Lawrence Eberhard, where you can actually explicitly evaluate these one loop diagrams. So maybe one could write down some reasonable one loop ansatz and then compare it to the block expansion in the next order in 1/n. And maybe you could fix it. So it'd be much harder, but it seems like it could be possible.
Anyone else? Yes, Soldrini.
So in this case of mixed flux, also there, did I understand correctly that the answer that you find is universal for T4 and K3, or does it?
It's universal, yes, because we're looking at the same universal correlate.
And you mentioned that it's because you're looking at this for modeling that.
Yeah. We're just looking at a specific half BPS multiplet, which happens to be universal for both. There's other half BPS multiplets I mentioned, which would be kind of more specific to T4.
Mm-hmm.
And there we also have an answer, but then that's specific to T4.
Is there any hope to reproduce this flat space expansion of this ADS Virasoro-Shapiro by doing like just computing the Green-Schwarz formula?
So okay, the Green-Schwarz formula. Okay, so I don't know about the Green-Schwarz formula. I don't know if people have ever been able to use the Green-Schwarz formulas to compute.
In flat space. I
Uh,
don't know if you can do it.
no, but I mean away from flat space. I'm not sure if people
You can expand around flat space.
So okay, my understanding from Dr. Sheehan is that it's not possible. Yeah, because I remember Arkady once was saying like, oh, maybe this should be possible, just very hard. Apparently Sheehan said it's actually impossible because apparently there's divergences that show up when you work on shell, and the only way to resolve them is to use string field theory. Although I mean I don't know the details.
The shift that was 2, 3, half, and 1 seems to be 2 times the number of supersymmetries divided by 32. Is there any reason?
Yeah, so that's an excellent observation. I don't really understand it. I mean, but yeah, that's indeed a very good observation, though. And yeah, I mean, it's probably, I mean, I don't know. So it's like, you know, so some vague speculation is that in the ADS5 case, when people compute this operator in integrability, it's kind of like a natural operator, I guess, in n = 4 language that people consider. And that operator isn't the superprimary, it's some descendant, which is shifted from the superprimary by 2 dimensions. And that's kind of the natural thing in integrability. And so when you compute that thing, it has shift 0, and thus the superprimary thus has shift 2 because it's 2 away from that thing. And so like maybe you could make some similar argument, like, yes, I don't know enough about the details of integrability in ABGM. Perhaps the operator they look at is also like naturally shifted from the superprimary by 3 halves. Although that would surprise me because they don't have to be some kind of Fermi. So I'm not sure, but yeah, there's probably some explanation of the sort you suggest.
Okay. I don't see anyone desperate to ask a question, so let's try again.